Among the countless stars that populate our vast universe, some worlds wander alone, without suns, without homes. These rogue planets drift through the cosmic darkness, carrying secrets of formation, survival, and maybe even life itself. In the depths of space, where light from distant stars barely reaches, these nomadic worlds journey in eternal night. They are the orphans of our galaxy, planets without a star to orbit, drifting silently through the void between solar systems. The concept seems almost haunting. Planetary bodies cast adrift, severed from the warmth and light that we associate with life and habitability. Imagine a planet like Jupiter, massive and mysterious, torn from its stellar parent, now traveling alone through interstellar space. Its swirling clouds of gas and enormous storms continuing their dance, but without the golden light of a sun to illuminate them. Or perhaps an Earth-sized world, its surface frozen solid in the absence of a warming star, yet possibly harboring heat and energy deep within its core. These are the rogue planets, also known as free-floating planets, nomad planets, or interstellar planets. They represent one of astronomy's most intriguing frontiers. The very concept challenges our traditional understanding of what a planet is. For centuries, we defined planets as worlds that orbit stars. Yet these rogues defy that definition, existing independently in the vast expanses between stellar systems. They force us to reconsider our cosmic categories, to expand our definitions beyond the familiar solar system model that has dominated our thinking since the time of Copernicus. How many of these lonely travelers might exist in our galaxy? Current estimates suggest they could number in the billions, perhaps even trillions. Some scientists propose there might be more rogue planets drifting between stars than there are planets orbiting stars. A stunning possibility that would reshape our cosmic perspective. Our galaxy might be filled with these wandering worlds, silently journeying through the darkness, unseen and unknown. The night sky above us may contain countless invisible worlds passing through our neighborhood, detected only by their subtle gravitational effects or the briefest moments when they pass in front of distant stars. Like ghosts in the cosmic machine, they move through our galaxy, influencing and being influenced by the stars and systems they pass near. The darkness surrounding these worlds does not diminish their importance. Rather, it enhances their mystery. What forces expelled them from their birth systems? Were they violently ejected through gravitational interactions with larger planets or passing stars? Or did they form in isolation, born outside the warm embrace of a stellar nursery? Could internal heat sources keep them warm despite the freezing temperatures of interstellar space, which can reach nearly negative 270 degrees Celsius? Might some harbor oceans beneath icy crusts? And could those oceans support life forms that have never known starlight? Picture a world where life evolved in darkness, where biological processes developed without photosynthesis, where creatures might navigate by the faint light of bioluminescence or through senses we can barely imagine. Such possibilities stretch our understanding of life's potential and adaptability to the extreme. As our technology advances, we are beginning to pierce the veil surrounding these elusive objects. Through specialized observational techniques, astronomers have detected several candidate rogue planets, offering tantalizing glimpses into their nature and prevalence. Each discovery adds another piece to the puzzle, helping us understand not just these wandering worlds, but the processes that shape planetary systems throughout the cosmos. Instruments like the James Webb Space Telescope and upcoming ground-based observatories promise to reveal more of these nomads, allowing us to study their atmospheres, compositions, and physical properties. We stand at the threshold of a new era in our understanding of these mysterious objects. These wandering worlds serve as natural laboratories for understanding planetary formation, evolution, and even the potential for life in the most extreme environments. They represent cosmic time capsules, preserving conditions that might have long ago changed in star-bound planetary systems. Free from the erosive effects of stellar radiation and unaffected by the complex dance of planetary siblings, these solitary travelers might maintain their original compositions and structures for billions of years. The story of rogue planets is also the story of our evolving understanding of the universe. Each new discovery challenges our preconceptions and expands our cosmic horizons. From the earliest days when we believed Earth was the center of all things, to our current understanding of a universe teeming with planets, many of which may drift alone through the void, our journey of discovery continues to surprise and humble us. In the coming hours, we will journey through the science, speculation, and significance of these nomadic planets. We will explore their origins, their physical characteristics, and the methods scientists use to detect and study them. We will consider their potential to harbor life and examine how they influence the dynamics of our galaxy. The study of rogue planets touches on fundamental questions about our universe. How do planetary systems form and evolve? How common is life in the cosmos? What secrets might be hidden on worlds far from the light of stars? These questions drive astronomers, planetary scientists, and astrobiologists in their quest to understand these enigmatic objects. As we contemplate these wanderers in the dark, we are reminded that the universe is vastly more complex and mysterious than we once imagined. That planets need not be bound to stars to exist. That worlds can journey alone through the cosmic sea, carrying their secrets across the ages. Join us now as we embark on an exploration of these fascinating objects, these planets without suns, these rogue worlds drifting through the great cosmic darkness. Their story is one of cosmic violence and serene isolation, of extreme environments and surprising possibilities, of questions that stretch our understanding and answers that might reshape our place in the universe. To understand rogue planets, we must first reconsider what we mean by the word planet itself. For most of human history, our definition was simple. Planets were the wandering lights in the night sky, distinct from the fixed stars. The word planet comes from the ancient Greek word for wanderer. Mercury, Venus, Mars, Jupiter, and Saturn were known to the ancients, visible to the naked eye, moving against the backdrop of stars. When Copernicus proposed his revolutionary model of the solar system in the 16th century, with the Sun at the center instead of Earth, our understanding shifted dramatically. Planets became worlds that orbit stars. This definition served astronomy well for centuries, as we discovered Uranus, then Neptune, and eventually Pluto, which was later reclassified as a dwarf planet. But nature, as always, defies our attempts at neat categorization. In the late 20th and early 21st centuries, astronomers began to seriously consider the possibility of planets that do not orbit stars at all. These would come to be known as rogue planets. A rogue planet, also called a free floating planet, interstellar planet, or nomad planet, is a planetary mass object that orbits the galaxy directly, unattached to any star. These are worlds adrift in the vast spaces between stellar systems, moving through the darkness of interstellar space. The first confirmed discovery of such an object came in 2013, when astronomers using infrared telescopes identified PSOJ 318.5-22, a gas giant roughly 6 times the mass of Jupiter, floating freely in space about 80 light-years from Earth. This discovery confirmed what many scientists had long suspected. Planets could exist beyond the warm embrace of stellar systems. Since then, astronomers have discovered more candidates. WISE J08 55+0714, which despite its technical designation, represents a profound discovery. A world approximately 5 times as massive as Jupiter, wandering through our galactic neighborhood. And CFB-DAFO 2308+0107, thought to be a binary system of 2 brown dwarfs, or perhaps a brown dwarf and a massive rogue planet. The boundary between brown dwarfs, which are failed stars too small to sustain hydrogen fusion in their cores, and massive rogue planets remains somewhat blurry. Generally, Objects with masses between about 13 and 75 times that of Jupiter are classified as brown dwarfs, while less massive objects are considered planets. But this distinction is based on theoretical mass limits rather than formation history, which can be difficult to determine for isolated objects. What makes these discoveries so remarkable is the inherent difficulty in finding rogue planets. Unlike stars, they emit almost no light of their own. Most planets we detect around other stars are found because they transit their host star, causing a tiny dip in the star's brightness, or because their gravitational pull causes their star to wobble slightly. Without a host star, these detection methods are useless for finding rogue planets. Instead, astronomers must rely on alternative approaches. One of the most successful has been gravitational microlensing. This phenomenon occurs when a massive object passes between Earth and a distant star or galaxy. The gravity of the intervening object acts like a lens, bending and magnifying the light from the background source. By carefully analyzing these microlensing events, scientists can determine whether the lensing object might be a rogue planet. Another approach relies on detecting the faint heat signature of young rogue planets. When first formed, planets retain heat from their formation process. This heat gradually radiates away over billions of years, but for relatively young planets, less than 100 million years old, this residual heat may be detectable in infrared wavelengths. Specialty telescopes that observe in infrared light, like the James Webb Space Telescope, are particularly valuable for this type of detection. The most massive rogue planets might also be detected through radio emissions generated by aurora-like phenomena. Just as Earth's magnetic field interacts with the solar wind to create the northern and southern lights, a rogue planet's magnetic field might interact with the interstellar medium to produce radio emissions detectable from Earth. Despite these ingenious detection methods, finding rogue planets remains enormously challenging. They are small, dark objects in the vast emptiness of space. The ones we have detected represent just the tip of the cosmic iceberg. The true population of rogue planets in our galaxy remains largely unknown. However, theoretical models and limited observational data suggest their numbers could be staggering. Some astronomers estimate that there might be billions or even trillions of rogue planets in the Milky Way alone. If these estimates are correct, rogue planets could outnumber stars in our galaxy by hundreds to one. A 2011 study suggested there might be 100,000 times more rogue Jupiter-sized planets than stars in the Milky Way. While this estimate has since been revised downward, the consensus remains that rogue planets are likely extremely common cosmic objects. Their prevalence raises profound questions about planet formation and evolution. Are most rogue planets ejected from their birth systems through gravitational interactions? Or do many form in isolation, perhaps in ways we have yet to fully understand? Current models of solar system formation suggest that planetary systems often begin as chaotic environments. Young planets interact gravitationally, sometimes resulting in collisions or near misses that can send worlds careening out of their systems entirely. Jupiter-sized planets, with their substantial gravitational influence, may be particularly effective at ejecting smaller worlds while remaining bound to their stars. The characteristics of rogue planets likely vary enormously. Gas giants like Jupiter consist primarily of hydrogen and helium, with no solid surface. Rocky planets like Earth have solid crusts surrounding molten mantles and cores. Ice giants like Uranus and Neptune contain substantial amounts of water, ammonia, and methane ices, in addition to rock and gas. All these planetary types could exist as rogues. Observations suggest that Jupiter-like gas giants are common among the rogue planet population, but this may be an observational bias. Larger objects are simply easier to detect at great distances. Smaller, Earth-sized rogue planets almost certainly exist, but detecting them presents even greater challenges. The composition of a rogue planet would largely be determined by its formation history. A planet born close to its star before being ejected would likely have a different composition than one formed at the outer edges of a stellar system. And both might differ from a planet that formed in isolation, never part of any solar system. For gas giants that have been ejected from their systems, their thick atmospheres might serve as effective insulation, trapping internal heat. These worlds might maintain relatively warm interiors for billions of years, despite the frigid temperatures of interstellar space. Rocky planets would cool more quickly, their surfaces freezing solid in the absence of stellar heating. But even these worlds might maintain some internal heat through radioactive decay in their cores, potentially enough to sustain liquid water beneath thick ice crusts, similar to what we observe on moons like Europa and Enceladus in our own solar system. Whatever their composition, rogue planets share one defining characteristic. They journey through the cosmos alone, untethered to any star, subject only to the gentle but inexorable pull of galactic gravity. Their orbits take them not around a central star, but around the galactic center itself, a journey of hundreds of millions of years. As they travel, they pass through varying environments. The galactic disk, dense with stars and interstellar clouds. The galactic halo, sparser, but still populated with globular clusters and ancient stars. And for some, perhaps even the vast emptiness of intergalactic space, should they be ejected from the Milky Way entirely. The discovery of rogue planets has revolutionized our understanding of what planetary systems look like and how they evolve. No longer can we think of planets as necessarily bound to stars. The traditional image of the solar system, with planets in neat near-circular orbits around a central star, represents just one possible configuration of worlds. Our galaxy is far more dynamic than once thought, with planets forming, migrating, being captured by and ejected from stellar systems throughout its history. The rogue planets drifting through interstellar space are testament to this dynamism, to the complex gravitational dance that shapes the architecture of our cosmic neighborhood. Though dark and lonely, rogue planets are more common than once thought. They represent not exceptions to the rule, but perhaps the most numerous type of planet in our galaxy. Far from being cosmic oddities, they may be the norm, outnumbering their starbound cousins many times over. In their silent journeys through the darkness, these nomads carry with them the potential to reshape our understanding of planetary science, to reveal new insights about the formation and evolution of worlds, and perhaps even to expand our conception of where life might find a foothold in the cosmos. Every rogue planet carries a story of birth, of escape, of survival. These stories are written in their composition, their mass, their temperature, and their motion through space. By understanding how rogue planets form, we gain insights not just into these wandering worlds themselves, but into the dynamic processes that shape planetary systems throughout our galaxy. There are several pathways through which a planet might become a cosmic nomad. The most commonly proposed mechanisms include ejection from a planetary system, formation in isolation, and formation around a star that later dies. Each origin story leaves distinctive signatures that astronomers might detect, given sufficiently advanced observational capabilities. Let us first consider ejection from a planetary system, perhaps the most dramatic origin for a rogue planet. When stars form, they are typically surrounded by a protoplanetary disk of gas and dust. Within these disks, planets begin to coalesce. First, tiny particles stick together to form pebbles. These pebbles grow into planetesimals, bodies a few kilometers across. And these planetesimals, in turn, merge to form protoplanets, which can eventually become full-fledged planets. This process of planetary formation is not neat and orderly. As multiple planets form within the same system, they interact gravitationally. These interactions can lead to orbital resonances, where the orbits of two or more bodies are related by a ratio of integers. Such resonances can be stable, as with the moons of Jupiter, or they can lead to instability over time. In unstable configurations, planets may experience close encounters with one another. During these encounters, gravitational forces can dramatically alter the orbits of the involved bodies. The most massive planet in such an encounter typically remains bound to the star, while less massive planets can be flung into highly eccentric orbits or ejected from the system entirely. Computer simulations suggest that this process of planetary ejection may be quite common, especially in systems with gas giants. A Jupiter-sized planet migrating inward can destabilize the orbits of smaller planets, sending some of them into interstellar space. Our own solar system may have once contained additional planets that were ejected during its early, more chaotic phase. The evidence for such ejections comes in part from the unusual orbits of some trans-Neptunian objects in our solar system, which suggest the influence of a now absent massive body. While this hypothetical Planet 9 might still exist in a distant orbit, another possibility is that it was ejected long ago, becoming one of the rogue planets now wandering our galaxy. Ejection need not occur only during the initial formation of a planetary system. Stellar encounters can also disrupt stable planetary systems. When two stars pass close to each other, their gravitational interaction can destabilize the orbits of their planets. In dense regions like star clusters, such encounters are more common, potentially leading to a higher rate of planetary ejections. The demographics of ejected planets would reflect the demographics of planets in stellar systems generally, though with some biases. Smaller, less massive planets are more easily ejected than larger ones. Gas giants like Jupiter are more likely to remain bound to their stars, while Earth-sized rocky planets are more vulnerable to ejection. However, the sheer number of small rocky planets in typical stellar systems might mean that they still constitute a significant fraction of the rogue planet population. A planet ejected from its star would carry with it atmospheric and compositional signatures of its prior home. A gas giant that formed beyond the snowline of its protoplanetary disk would have a different composition than one that formed closer to its star. These differences might be detectable with sufficiently advanced spectroscopic observations. The age of an ejected planet would correspond roughly to the age of its parent star, though determining this age for a rogue planet presents obvious challenges. However, measurements of isotopic ratios or atmospheric composition might provide clues about when the planet formed. If a planet is ejected soon after its formation, it might still be quite warm from the heat of its formation process. If ejected later, after billions of years orbiting its star, it would have already cooled significantly. This difference in thermal state might be detectable through infrared observations. The velocity and trajectory of a rogue planet through the galaxy could also provide clues about its origin. A planet ejected from a system within the galactic disk would initially share the motion of its parent star. Over time, interactions with other stars and the galactic gravitational field would alter its path, but some signature of its origin might remain in its velocity vector. While ejection from a planetary system is perhaps the most intuitive origin for rogue planets, it is not the only possibility. Some rogue planets may form in isolation, never orbiting a star at all. This process might occur in several ways. In the dense molecular clouds where stars form, not all collapsing regions of gas and dust accumulate enough mass to ignite nuclear fusion and become stars. Some collapse only partially, forming objects known as brown dwarfs. These failed stars have masses between about 13 and 75 Jupiter masses, too small to sustain hydrogen fusion in their cores. Below the brown dwarf mass range, we find objects that might be considered planets. Just as a cloud of gas can collapse to form a star, smaller pockets of gas might collapse to form planetary mass objects directly. These would not be planets in the traditional sense of having formed around a star, but they would have planetary masses and compositions. The boundary between brown dwarfs and gas giant planets is somewhat blurry. Both can have similar masses and compositions. The traditional distinction is based on formation pathway, with brown dwarfs forming like stars through direct collapse of gas clouds, and planets forming through accretion in protoplanetary disks. But for isolated objects with no formation history to observe, this distinction becomes less meaningful. Some astronomers have proposed that free-floating planetesimals might grow through accretion of dust and gas from the interstellar medium. This would be an extremely slow process compared to formation in a protoplanetary disk, but given enough time, it could potentially result in planetary mass objects. Another possibility involves the fragmentation of protoplanetary disks. Under certain conditions, regions of a disk might break apart and form bound objects separate from the main system. If these fragments do not accrete enough mass to become brown dwarfs, they might instead become rogue planets. The signatures of isolated formation would differ from those of ejection. Planets formed in isolation would never have experienced the warmth of a nearby star. Their atmospheres would not show signs of stellar irradiation. Their compositions might reflect the composition of the interstellar medium at their formation location, rather than the more processed material of a protoplanetary disk. Isolated formation is likely more common for gas giant rogue planets than for rocky ones. The direct collapse of a gas cloud is more likely to produce an object with a composition similar to Jupiter than one similar to Earth. The formation of rocky planets generally requires the higher densities and temperatures found in the inner regions of protoplanetary disks. A third potential origin for rogue planets involves the death of stars. When a star like our Sun exhausts its nuclear fuel, it expands into a red giant before eventually ejecting its outer layers and leaving behind a white dwarf. This process can disrupt the orbits of planets in the system. Some planets might be engulfed by the expanding star. Others might survive, but have their orbits altered significantly. In some cases, planets might be ejected entirely, becoming rogue planets. Unlike planets ejected during the formation phase of a stellar system, these would be older, having potentially orbited their star for billions of years before being cast adrift. More dramatic stellar deaths, such as supernova explosions, can also lead to the liberation of planets. When a massive star explodes as a supernova, it can eject more than half its mass in a matter of seconds. This sudden mass loss can unbind planets from their orbits, sending them into interstellar space. Planets ejected by dying stars would carry signatures of their long tenure in a stellar system. Rocky planets might show evidence of billions of years of stellar irradiation. Gas giants might have atmospheres processed by the radiation of their former stars. Both would likely be older than the average rogue planet formed through other mechanisms. The study of rogue planets and their origins connects to broader questions in astronomy. The frequency of planetary ejections provides insights into the stability of planetary systems. The existence of planets formed in isolation challenges our understanding of planet formation. And planets ejected by dying stars offer a glimpse into the ultimate fate that may await worlds in our own solar system billions of years in the future. As observations of rogue planets improve, we may be able to distinguish between these different origin stories. The James Webb Space Telescope, with its unprecedented infrared sensitivity, promises to detect and characterize more rogue planets than ever before. Future missions and ground-based observatories will build on this work, gradually unveiling the origins of these cosmic wanderers. The birth stories of rogue planets remind us that the cosmos is in constant flux. Stars form and die. Planets migrate, collide, and sometimes escape. Systems that appear stable on human timescales may be anything but when viewed across billions of years. The rogue planets drifting through interstellar space are not anomalies, but inevitable products of these cosmic processes. In their journeys through the dark expanses between stars, rogue planets carry the history of their formation and escape. They are time capsules, preserving conditions from their birth systems or the regions of interstellar space where they formed. And in their solitary paths through the galaxy, they embody the profound dynamism of our cosmic neighborhood. What is it like on a rogue planet to stand on a world without a sun, drifting through the vast emptiness between stars? The environment of a rogue planet presents one of the most extreme and alien landscapes imaginable, yet understanding these conditions is crucial for assessing their potential significance in our galaxy. The most immediately obvious feature of a rogue planet is the darkness. Without a nearby star, the surface of a rogue planet would experience perpetual night. The only illumination would come from distant stars, perhaps appearing as faint pinpricks of light in an otherwise black sky. The brightness would be far less than what we experience on a moonless night on Earth. If the rogue planet happens to be passing through a dense star cluster or near the galactic center, the starlight might be somewhat brighter, but still extraordinarily dim by earthly standards. For a rogue planet with a moon, the satellite might provide periodic illumination as it reflects the faint starlight. But this would be minimal compared to the moonlight we experience on Earth. Any surface features would be shrouded in shadow, visible only to instruments capable of detecting infrared radiation or through artificial lighting brought by hypothetical explorers. The second defining characteristic of a rogue planet environment is the cold. Without stellar heating, the surface temperature of a rogue planet would approach the background temperature of space itself, around -270 degrees Celsius, just a few degrees above absolute zero. At such temperatures, most gases would freeze solid. Any water, methane, or ammonia on the surface would exist as rock-hard ice. However, the actual temperature of a rogue planet depends on several factors, including its age, mass, composition, and the presence of internal heat sources. Planets retain heat from their formation for billions of years, gradually radiating it away into space. The larger the planet, the more heat it would have accumulated during formation and the longer it would take to cool. For massive gas giants wandering through interstellar space, internal temperatures could remain quite high even after billions of years. Jupiter, for instance, radiates more heat than it receives from the Sun, indicating significant internal heat generation. A Jupiter-sized rogue planet might maintain an internal temperature of thousands of degrees Celsius, though its outer layers would still be extremely cold. Several mechanisms contribute to this internal heating. Gravitational contraction, the process by which gravity compresses a planet and converts potential energy to heat, continues long after formation, especially in gas giants. Radioactive decay of elements like uranium, thorium, and potassium provides another heat source, more significant in rocky planets than in gas giants, due to the higher concentration of these elements in rocky materials. Perhaps most intriguingly, tidal heating could warm rogue planets that have large moons or that are part of a rogue binary planet system. The gravitational interaction between two closely orbiting bodies generates friction within their interiors, converting orbital energy into heat. This process powers the extraordinary volcanic activity on Jupiter's moon Io and likely maintains the subsurface ocean on another Jovian moon, Europa. A rogue planet with a substantial moon might experience enough tidal heating to maintain significant internal warmth, potentially creating environments where liquid water could exist beneath an icy surface. This possibility becomes especially relevant when we consider the potential for life on these wandering worlds. The atmospheric conditions on a rogue planet would vary enormously depending on its mass, composition, and thermal state. A massive gas giant rogue planet would retain most of its original atmosphere, with hydrogen and helium dominating its composition. Such an atmosphere might extend thousands of kilometers above the denser core, creating immense pressure as one descended toward the planet's center. Rocky rogue planets present a different scenario. Without the warming effect of a star, most gases would freeze out of the atmosphere, condensing as ice on the surface. Carbon dioxide, water vapor, and other volatiles would exist primarily in solid form. Only gases with extremely low freezing points, like hydrogen, helium, and to some extent neon, might remain in the atmosphere, and even these would be greatly reduced compared to their abundance on warmer worlds. However, atmospheric retention also depends on a planet's mass and the resulting gravitational field. Larger rocky planets might hold onto a thin atmosphere of the lightest elements even at extremely cold temperatures. And if internal heating keeps part of a rogue planet's interior warm, outgassing from the interior could periodically replenish the atmosphere. One fascinating possibility is a periodic or cyclical atmosphere on a rogue planet with significant internal heating. Volcanic or geothermal activity might release gases that temporarily create a denser atmosphere before they gradually freeze out again as they radiate heat to space. This could create a dynamic environment with atmospheric pressure and composition varying over time. Without stellar wind and radiation, the upper atmosphere of a rogue planet would not experience the same erosion processes that affect planets orbiting stars. This might allow even relatively small rogue planets to retain whatever traces of atmosphere they possess for longer periods than their starbound counterparts. The surface of a rogue rocky planet would be shaped by different processes than those we observe on Earth. Without liquid water or a significant atmosphere, there would be no erosion from rain, rivers, or wind. Without the daily heating and cooling cycle driven by a parent star, there would be no thermal expansion and contraction to crack rocks. Instead, the surface would be modified primarily by impacts from space debris, by tectonic activity driven by internal heating, and perhaps by the freezing and thawing of subsurface materials if internal temperatures fluctuated enough to permit such phase changes. The absence of weathering would preserve surface features for extraordinarily long periods. Impact craters would remain sharp and well-defined for billions of years. Volcanic features would appear almost as fresh as when they formed. The surface would record a history of geological activity unmarred by the erasure that weathering causes on Earth. For gas giant rogue planets, there is no solid surface in the conventional sense. Instead, as one descended through the atmosphere, the gas would gradually become denser until it transitioned into a liquid-like state, then perhaps into exotic forms of matter under extreme pressure. The visible outer layers would consist of swirling clouds of various compositions, their movements driven by the planet's rotation and internal heat, rather than external heating from a star. Without stellar heating to drive weather patterns, the atmospheric circulation on a rogue planet would be powered entirely by internal heat. For gas giants with substantial internal energy, this could still create dramatic weather systems. Jupiter, which generates more than twice as much heat through its internal processes as it receives from the Sun, exhibits some of the most violent storms in our solar system, including the Great Red Spot, a storm that has persisted for at least 400 years. A gas giant rogue planet might display similar storm systems, with bands of clouds circulating at different speeds, massive cyclonic storms where different bands interact, and lightning generated by charge separation in cloud layers. These weather patterns would evolve more slowly than on star-heated planets, driven by the more gradual release of internal heat, rather than the daily cycle of stellar heating. One of the most intriguing aspects of rogue planet environments is the possibility of subsurface oceans. On a rocky or icy rogue planet with sufficient internal heating, the combination of internal warmth and the insulating effect of an ice crust could maintain liquid water beneath the surface. The thicker the ice crust, the more effectively it would insulate the water below, preventing heat from escaping to space. We observe this phenomenon in our own solar system. Europa, a moon of Jupiter, has a global subsurface ocean despite its great distance from the Sun. The ocean remains liquid due to tidal heating from Jupiter and the insulating effect of Europa's ice crust. Similar subsurface oceans are thought to exist on several other outer solar system bodies, including Enceladus, Ganymede, and possibly Pluto. A rogue planet with sufficient mass and internal heating could maintain such an ocean for billions of years, completely independent of any stellar heating. This ocean would be dark, with no sunlight penetrating the ice crust above it. But it would not necessarily be static or lifeless. Hydrothermal vents, where geothermally heated water rich in minerals emerges from the ocean floor, could provide energy sources for potential ecosystems, just as they do in Earth's deep oceans. The magnetic field of a rogue planet would provide another important aspect of its environment. Generated by the movement of conductive fluids in a planet's interior, magnetic fields extend into space around a planet, deflecting charged particles and creating a protective bubble. Earth's magnetic field shields us from the solar wind, preventing our atmosphere from being stripped away by this stream of charged particles from the sun. For a rogue planet, there is no solar wind to defend against, but the interstellar medium still contains charged particles that a magnetic field would deflect. More importantly, a magnetic field provides evidence of a dynamic, partially molten interior, which in turn suggests internal heating sufficient to potentially maintain subsurface liquid water. The detection of a magnetic field around a rogue planet would be a significant discovery, potentially indicating conditions amenable to habitability. Current observational techniques make detecting such fields challenging, but future advancements might make it possible to sense the magnetic fields of relatively nearby rogue planets. The radiation environment on a rogue planet would differ significantly from that experienced by planets orbiting stars. Without a nearby star producing a continuous flux of ultraviolet light and charged particles, the radiation would come primarily from cosmic rays, high-energy particles originating from outside our solar system and from any radioactive elements within the planet itself. Cosmic rays would penetrate more deeply into the atmosphere or surface of a rogue planet than they do on Earth, where our magnetic field and atmosphere provide substantial protection. Any theoretical organisms on the surface of a rogue planet would need protection from this radiation, perhaps through adaptations like efficient DNA repair mechanisms or by living beneath the surface. Despite the seemingly harsh conditions, the environment of a rogue planet need not be static or unchanging over its lifetime. As it drifts through the galaxy, a rogue planet would pass through regions of varying density, from the near vacuum of galactic voids to the relatively denser environment of molecular clouds or star clusters. During these passages, conditions could change dramatically. A rogue planet passing through a dense molecular cloud might accumulate additional material, temporarily thickening its atmosphere or depositing new compounds on its surface. One passing near a star might experience a brief period of warming, potentially triggering cycles of freezing and thawing in its outer layers. Over the course of billions of years, a rogue planet might occasionally pass close enough to a star to be captured into orbit, ending its wandering phase and becoming a conventional planet once more. Conversely, a planet orbiting a star might be ejected through gravitational interactions, beginning a journey as a rogue. The boundary between rogue and conventional planets is not fixed, but permeable over astronomical timescales. The vast majority of a rogue planet's existence would be spent in the cold darkness between stars. But this does not mean these environments are without importance or significance. The internal heat sources that might keep parts of these worlds warm could also drive chemical reactions, energy flows, and potentially even biological processes. Even in eternal night, the environments of rogue planets might harbor more complexity and dynamism than we might initially imagine. And in their long, solitary journeys through interstellar space, they might preserve conditions that have long since changed in more dynamic starbound systems. Could life exist on a world without a sun? This question stretches our understanding of habitability and challenges our preconceptions about the conditions necessary for life. For most of scientific history, the answer would have been a definitive no. Life, we assumed, requires energy from sunlight, temperate conditions, and liquid water. A rogue planet, drifting through the frigid darkness of interstellar space, would seem to offer none of these. Yet, our exploration of extreme environments on Earth and our growing understanding of the outer planets and moons in our own solar system have dramatically expanded our conception of where life might take hold. Organisms on Earth thrive in acid, in boiling water, in frozen lakes, in rocks kilometers beneath the surface, and in the crushing depths of the ocean. Life, it seems, is remarkably adaptable, finding niches in environments once thought completely inhospitable. This adaptability opens the possibility, however remote, that life might exist even on rogue planets. To assess this possibility, we must consider what life requires at its most fundamental level, and whether rogue planets could provide these necessities. All known life requires three basic components. First, a solvent in which chemical reactions can occur. On Earth, this solvent is liquid water. Second, a source of energy to drive metabolic processes. And third, essential chemical building blocks, particularly carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, the elements that make up DNA, proteins, and the other molecules of life. Let us consider each of these requirements in the context of rogue planets. The most crucial, and perhaps most surprising, is liquid water. While the surface of a rogue planet would be frozen solid, we have already discussed the possibility of subsurface oceans maintained by internal heating. The moons Europa and Enceladus in our own solar system demonstrate that bodies far from the Sun can maintain liquid water beneath their icy crusts, warmed by a combination of tidal forces and radioactive decay. A massive rogue planet with a large moon, or a pair of rogue planets orbiting each other, could experience similar tidal heating. The gravitational dance between these bodies would convert orbital energy into heat, potentially enough to maintain liquid water beneath an insulating layer of ice. Even without tidal heating, larger rogue planets might retain enough primordial heat or generate enough through radioactive decay to keep subsurface water liquid for billions of years. The thickness of the ice crust would depend on the amount of internal heating and the planet's distance from its former star before ejection, if it had one. A planet that formed closer to its star would have less surface ice to begin with, and might maintain a thinner ice crust even after ejection. A more massive planet with greater internal heating would also tend to have a thinner ice layer. Estimates suggest that a super-Earth-sized rogue planet with 5 to 10 times the mass of our world could maintain a subsurface ocean beneath as little as 10 to 20 kilometers of ice. For comparison, the deepest point in Earth's oceans, the Challenger Deep in the Mariana Trench, is nearly 11 kilometers below sea level. Drilling or melting through 20 kilometers of ice presents an enormous engineering challenge for human exploration, but would not necessarily be an insurmountable barrier for life that originated when the ocean was in contact with the surface, before the planet was ejected from its star system. The second requirement for life is an energy source. Without sunlight, photosynthesis as we know it would be impossible on a rogue planet. But photosynthesis is not the only way organisms can obtain energy. On Earth, entire ecosystems exist around hydrothermal vents on the ocean floor where no sunlight penetrates. These communities rely on chemosynthesis, a process where microbes derive energy from chemical reactions, particularly the oxidation of hydrogen sulfide or methane released from the vents. Similar energy sources could exist on rogue planets with subsurface oceans. Geological activity driven by internal heating could create hydrothermal systems where water interacts with rock, generating energy-rich chemical compounds. The interface between water and rock could provide chemical gradients that organisms might exploit for energy. Radiolysis offers another potential energy source. This process occurs when radiation splits water molecules into hydrogen and oxygen. On Earth, some microorganisms can utilize the hydrogen produced by radiolysis of water by radioactive minerals. In a subsurface ocean on a rogue planet, radiation from radioactive elements in the core or mantle could split water molecules, providing a steady, if modest, source of chemical energy. The necessary chemical building blocks for life present the third requirement. Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, the so-called CETNOPS elements, are among the most abundant in the universe. A rogue planet, whether formed in a protoplanetary disk before ejection or condensed directly from a molecular cloud, would likely contain all these elements in significant quantities. Organic compounds, including those thought to be precursors to life, have been detected throughout the cosmos, in interstellar clouds, comets, and meteorites. Some of the most complex prebiotic chemistry we have observed occurs in the cold, radiation-processed ices of comets and other outer solar system bodies. The surface ice of a rogue planet might host similar chemistry, potentially generating complex organic compounds. If a rogue planet originated as part of a star system before being ejected, it might have already developed a rich inventory of organic compounds during its time in orbit. These compounds could include amino acids, nucleobases, and other building blocks of life. Even after ejection, cosmic rays and internal radiation could continue to drive chemical reactions in the planet's ice, potentially increasing molecular complexity. The interface between rock and water in a subsurface ocean would be particularly important for life. Minerals can catalyze chemical reactions, concentrate organic compounds, and provide surfaces where molecules can organize themselves. The chemistry at such interfaces might be complex enough to give rise to self-replicating systems, the precursors to true life. Given these considerations, we can envision several scenarios for life on rogue planets. The first, and perhaps most plausible, involves a planet that developed life while still orbiting its star, before ejection into interstellar space. Microbial life in subsurface oceans might survive the ejection process, adapting to the loss of solar energy by shifting to chemosynthetic metabolisms if it had not already done so. The frozen surface would provide protection from the radiation of interstellar space, while the thick ice crust would insulate the ocean, preventing it from freezing. Life might continue to evolve in this subsurface environment, perhaps for billions of years, completely isolated from the rest of the universe. What forms might such life take? Most likely single-celled organisms, comparable to Earth's bacteria and archaea, particularly those adapted to cold, dark environments. These might form mats or colonies around hydrothermal vents or other energy sources. Given enough time and the right conditions, more complex multicellular organisms might evolve, perhaps analogous to the tube worms, crabs, and blind shrimp found around Earth's deep sea vents. Without sunlight, such organisms would rely on other senses. Bioluminescence, the production of light through biochemical reactions, might evolve as a means of communication, attracting mates or luring prey. Some deep-sea creatures on Earth use bioluminescence for these purposes, creating their own light in an environment without sun. Touch and the detection of vibration would be important senses in a liquid environment. Chemical sensing, analogous to taste and smell, would help organisms locate food sources and avoid toxins. Some might develop electrical sensing abilities like those of sharks and certain fish on Earth, useful for detecting the electrical fields generated by other organisms or by geological processes. A second scenario for life on rogue planets involves the spontaneous origin of life on the rogue planet itself after ejection. While more speculative, this possibility cannot be dismissed entirely. If the conditions discussed above, liquid water, energy sources, and organic building blocks, persisted for billions of years, the chemical reactions necessary for life might occur. The process would likely be slower than on a planet with abundant solar energy, but time is one resource the universe has in abundance. The interface between ice and liquid water could provide an interesting environment for the origin of life. Laboratory experiments suggest that freezing can concentrate organic compounds, bringing them close enough to react with each other. The slow freezing and occasional thawing of water near the upper boundary of a subsurface ocean might create conditions conducive to the formation of complex organic molecules. A third scenario introduces an even more speculative possibility. Perhaps some forms of life could exist not in liquid water, but in other solvents that remain liquid at the extremely low temperatures of a rogue planet's surface. Compounds like methane and ethane become liquid at temperatures far below the freezing point of water. On Saturn's moon Titan, lakes and seas of liquid methane and ethane exist on the surface, raising the question of whether some form of life might use these hydrocarbons as solvents. Such life would be based on very different chemistry than Earth life. It would likely use silicon rather than carbon as its structural element, as silicon forms strong bonds with itself in extremely cold conditions, where carbon-based molecules become rigid. Its metabolic processes would be extraordinarily slow by Earth standards due to the low temperatures, with chemical reactions proceeding at a glacial pace. Whether such exotic life forms could actually exist remains highly speculative. But the incredible diversity of life on Earth and the growing evidence for liquid environments on outer solar system bodies encourage us to keep an open mind about the possibilities. The potential for life becomes even more intriguing when we consider the sheer number of rogue planets that might exist in our galaxy. If current estimates are correct, rogue planets outnumber stars by a significant margin. Even if only a small fraction of these possess the conditions necessary for life, the total number of potentially habitable rogue worlds could be staggering. This raises a provocative question. Could rogue planets, rather than conventional planets orbiting in habitable zones around stars, harbor the majority of life in our galaxy? It seems counterintuitive, given our sun-centered view of habitability. But the mathematics of large numbers forces us to consider the possibility. If rogue planets outnumber conventional planets by a factor of 100 or more, then even if only 1 in 1,000 rogue planets has conditions suitable for life, they could collectively host more biological activity than all starbound worlds combined. Life on rogue planets would face unique challenges and opportunities. Without a day-night cycle or seasons to mark the passage of time, organisms would need different ways to regulate their biological processes. Without photosynthesis, ecosystems would be limited by the availability of chemical energy, constraining the total biomass that could be supported. Yet there would also be advantages to life on a rogue planet. Without stellar radiation, organisms would be protected from the harmful effects of ultraviolet light and stellar flares. The stable conditions in a subsurface ocean, unchanging over billions of years, might allow for very gradual, uninterrupted evolution. And without the eventual death of a parent star to contend with, life on a rogue planet might persist for extraordinarily long periods, perhaps tens of billions of years, far longer than would be possible on a planet orbiting a star. This longevity presents another intriguing possibility. If technological civilizations could arise on rogue planets, an admittedly remote possibility, they might have motivations and perspectives very different from our own. A civilization that evolved in darkness might develop advanced technologies for generating and using energy efficiently. They might master nuclear fusion or tap into the rotational energy of their planet. Having never seen the stars, they might not develop astronomy until a very advanced technological stage, when they could detect cosmic rays or neutrinos. Their philosophy and worldview would surely differ from our own in fascinating ways. Without visible stars or a broader cosmos to observe directly, how would they conceive of their place in the universe? Would they develop entirely different mythologies and scientific paradigms based on their unique environment? These speculations, while engaging, take us far beyond what we can scientifically assess with current knowledge. Yet they illustrate the profound implications of the possibility of life on rogue planets. If life can exist in such extreme environments, disconnected from the warming light of stars, then the potential habitats for life in the universe expand enormously. And our conception of what life is and where it can thrive must expand accordingly. The search for life on rogue planets presents enormous technical challenges. These objects are dim, cold, and difficult to detect, let alone study in detail. Yet future astronomical capabilities may allow us to identify rogue planets with subsurface oceans by detecting water vapor or other gases that escape through cracks in their icy shells, creating tenuous atmospheres. Magnetic fields generated by salty subsurface oceans might also be detectable with sufficiently sensitive instruments. For now, the possibility of life on rogue planets remains theoretical, a fascinating conjunction of what we know about extreme life forms on Earth and what we are learning about the potential environments of planets adrift in interstellar space. But the mere possibility expands our understanding of habitability and reminds us that life, with its remarkable adaptability, might find footholds in environments we can barely imagine. Indeed, life's tenacity may extend far beyond sunlit worlds. In the dark, frozen deserts of rogue planets, beneath kilometers of ice, warmed by the faint glow of radioactive decay or the gravitational embrace of a moon, the chemistry of life might even now be unfolding in patterns both familiar and utterly alien. The great cosmic sea, it seems, may harbor more possibilities for life than we have yet dreamed. To unlock the secrets of rogue planets, we must first find them. This presents one of the most formidable challenges in modern astronomy. Unlike stars that shine brightly across vast cosmic distances, or planets that reveal themselves through their effects on parent stars, rogue planets drift through space in near-perfect darkness, emitting almost no light of their own. They are cosmic ghosts, influencing their surroundings primarily through gravity, their presence often inferred rather than directly observed. Yet despite these difficulties, astronomers have developed ingenious methods to detect and study these elusive objects. Each approach has its strengths and limitations, and together they are gradually lifting the veil on the population of rogue planets in our galaxy. The most successful technique for detecting rogue planets has been gravitational microlensing. This phenomenon occurs when a massive object passes between an observer and a distant light source, typically a star. According to Einstein's general theory of relativity, mass curves space-time, causing light passing near the mass to follow this curved path. The intervening object acts as a lens, temporarily magnifying and distorting the light from the background source. For massive objects like stars, this lensing effect can be substantial, creating multiple images or ring-like distortions of the background source. For less massive objects like planets, the effect is much subtler, causing a brief brightening of the background star that might last from a few hours to a few days, depending on the mass of the lensing object and the relative velocities involved. By carefully measuring the characteristics of these microlensing events, astronomers can determine the mass of the lensing object. If the mass falls within the planetary range, roughly 0.1 to 13 Jupiter masses, and no parent star is detected nearby, the object might be classified as a rogue planet. Several large-scale surveys have used microlensing to search for rogue planets. The Optical Gravitational Lensing Experiment, or OGLE, has been monitoring millions of stars in the direction of the galactic bulge since 1992, looking for brightness variations caused by microlensing. The Microlensing Observations in Astrophysics, or MOA, project uses a 1.8-meter telescope in New Zealand for similar observations. These surveys have yielded tantalizing results. A 2011 analysis of microlensing data suggested an enormous population of Jupiter-mass rogue planets, potentially outnumbering stars in the Milky Way by orders of magnitude. Subsequent studies have revised these estimates downward, but still indicate a substantial population of free-floating planets. However, microlensing has significant limitations as a detection method. Most importantly, it is a one-time event. Once the alignment between the observer, the lensing object, and the background source passes, the effect disappears, and the rogue planet returns to invisibility. This makes follow-up observations extremely difficult, if not impossible. We cannot return to study the same object in more detail, as we can with stars or planets orbiting stars. Additionally, microlensing typically provides only limited information about the detected object. We can estimate its mass, but details about its composition, temperature, age, and other characteristics remain elusive. And because microlensing events are rare, requiring precise alignments, building a statistical understanding of the rogue planet population through this method alone is challenging. Despite these limitations, microlensing remains our most powerful tool for detecting the lower mass end of the rogue planet spectrum, particularly Earth mass and super-Earth mass objects. Future space-based microlensing surveys, such as the Nancy Grace Roman Space Telescope, will significantly increase our sensitivity to these events and should provide a much clearer picture of the full mass distribution of rogue planets. For more massive rogue planets, particularly young ones that still retain significant heat from their formation, direct detection becomes possible through infrared observations. All objects emit thermal radiation based on their temperature. For rogue planets, which typically have temperatures of less than a few hundred Kelvin, this radiation peaks in the infrared part of the spectrum. young gas giant rogue planets, less than 100 million years old, may still be warm enough, with temperatures around 1000 Kelvin, to be detected by powerful infrared telescopes. This approach has led to the discovery of several candidate rogue planets in young star clusters, where recently formed planets might have been ejected but have not yet had time to cool significantly. The Subaru Strategic Program conducted with the Hyper-SuPrime CAM on the Subaru telescope has identified several candidate rogue planets in the Upper Scorpius star-forming region, approximately 5 million years old. These objects have masses similar to Jupiter, but no detectable host stars. Similarly, infrared surveys with the Very Large Telescope in Chile have identified objects like CFB-D SIR 2149-0403, a young gas giant that appears to be associated with the AB Doradus Moving Group, a collection of stars that formed together about 120 million years ago. Though initially thought to be a rogue planet, subsequent observations have raised questions about whether this object is actually associated with the moving group, illustrating the challenges of confirming rogue planet candidates. The James Webb Space Telescope, with its unprecedented infrared sensitivity, promises to revolutionize the direct detection of rogue planets. It should be able to detect and characterize much cooler and older rogue planets than previous instruments, potentially identifying objects down to a few times the mass of Earth in nearby star-forming regions. Direct detection in the infrared offers several advantages over microlensing. Most importantly, it allows for repeated observations of the same object, enabling detailed studies of its characteristics. Through spectroscopy, astronomers can analyze the composition of the planet's atmosphere, if present, and gather clues about its formation history and current conditions. However, direct detection also has significant limitations. As rogue planets age, they cool rapidly, becoming increasingly difficult to detect. A billion-year-old Jupiter-mass rogue planet would have a temperature of only about 100 Kelvin, making it practically invisible except to the most sensitive infrared instruments, and only if it is relatively close to our solar system. Earth-mass rogue planets would be cooler still and nearly impossible to detect directly with current technology unless they are exceptionally young or unusually warm due to internal heating processes. Another promising approach for detecting rogue planets involves radio astronomy. Some gas giant planets, including Jupiter in our own solar system, generate strong radio emissions through interactions between their magnetic fields and charged particles. These emissions are produced when electrons spiral along magnetic field lines, generating what is known as cyclotron radiation. If massive rogue planets have strong magnetic fields, they might produce similar radio emissions through interactions with the interstellar medium. These emissions could potentially be detected by sensitive radio telescopes, particularly for relatively nearby rogue planets. The Low-Frequency Array, or LOFAR, and the upcoming Square Kilometre Array, or SKA, have the sensitivity to potentially detect such emissions. This approach would be particularly valuable because it could identify rogue planets regardless of their age, as the radio emissions depend on the planet's magnetic field strength rather than its temperature. A strong magnetic field also implies a rapidly rotating, partially liquid interior, which in turn suggests internal heating, sufficient to potentially maintain conditions suitable for life. Thus, radio detection might preferentially identify some of the most interesting rogue planets from a habitability perspective. Beyond these primary detection methods, astronomers are exploring other innovative approaches. One possibility involves looking for occultations, events where a rogue planet passes in front of a background star as seen from Earth, temporarily blocking its light. Unlike microlensing, which relies on the gravitational effect of the planet, occultations depend on the physical size of the object crossing our line of sight to the star. The challenge with this approach is the extremely low probability of such precise alignments. However, large-scale surveys monitoring millions of stars simultaneously, such as the Vera C. Rubin Observatory with its legacy survey of space and time, might capture enough of these rare events to contribute meaningfully to our understanding of the rogue planet population. For the nearest rogue planets, astrometric detection might become possible with future instruments. This approach would measure the tiny gravitational effect of a passing rogue planet on nearby stars, detecting its presence through the slight wobble it induces in stellar positions. The European Space Agency's Gaia mission, which is creating the most precise three-dimensional map of our galaxy ever constructed, might detect the largest and closest rogue planets through this method. Once a rogue planet has been detected, characterizing it presents another set of challenges. For directly detected objects, spectroscopic observations can reveal the composition of any atmosphere the planet might retain. Different molecules absorb light at characteristic wavelengths, creating a spectral fingerprint that astronomers can identify. Methane, water vapor, carbon dioxide, and other compounds might be detected in the atmospheres of young, massive rogue planets. The presence and composition of an atmosphere can provide crucial information about a rogue planet's origin and history. A planet that formed as part of a stellar system before being ejected might retain an atmosphere similar to comparable planets still orbiting stars. One that formed in isolation might have a different atmospheric composition, reflecting the materials available in the interstellar medium rather than in a protoplanetary disk. For rocky rogue planets, any atmosphere would likely be minimal, having frozen onto the surface once the planet was ejected from its stellar system. But even tenuous atmospheres can be informative. Outgassing from the interior might periodically replenish certain compounds, potentially creating a detectable signature that could reveal ongoing geological activity. Determining the mass of directly detected rogue planets presents particular difficulties. For planets orbiting stars, mass can be calculated from the gravitational effect on the parent star or on other planets in the system. For isolated objects, such reference points are missing. Estimates must rely on theoretical models relating the planet's observed brightness and spectrum to its mass, introducing significant uncertainties. In some cases, rogue planets might be found as binary systems, two planets orbiting each other in the absence of a star. Such systems would be immensely valuable for study, as the orbital parameters would allow precise determination of the masses of both objects. Several candidate binary brown dwarfs have been discovered, and it is likely that binary rogue planets also exist, though none have been definitively identified yet. The age of rogue planets presents another challenging characteristic to determine. For planets in stellar systems, the age can usually be estimated from the age of the parent star, which can be determined through various methods including stellar evolution models. For rogue planets, without this reference point, age estimation becomes much more uncertain. Young rogue planets might be identified through association with known star clusters or moving groups, collections of stars that formed together and still move through space in roughly the same direction. If a rogue planet appears to share the motion of such a group, it likely formed at the same time and was subsequently ejected, giving astronomers an approximate age. For older rogue planets not associated with any stellar group, age estimation must rely on cooling models. As a planet ages, it radiates away its internal heat and cools at a rate determined by its mass and composition. By measuring the current temperature of a rogue planet and applying theoretical cooling models, astronomers can estimate how long the planet has been cooling and thus its approximate age. The trajectory of a rogue planet through the galaxy can also provide clues about its origin and history. The motion of stars in the Milky Way is not random, but follows patterns related to their age and the location of their formation. Similarly, the velocity and direction of a rogue planet's journey might indicate whether it was ejected from the galactic disk, where most stars form, or has a more exotic origin. The fastest rogue planets might be those ejected through interactions with supermassive black holes at the centers of galaxies. Such interactions could accelerate planets to velocities of hundreds or even thousands of kilometers per second, potentially fast enough to escape the galaxy entirely. these hypervelocity rogue planets would represent some of the most extreme objects in our cosmic neighborhood. Looking to the future, the most promising advances in rogue planet detection and characterization will come from a combination of new observational facilities and improved theoretical models. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct a microlensing survey of unprecedented sensitivity, potentially detecting thousands of rogue planets down to the mass of Mars, or even smaller. The James Webb Space Telescope, with its revolutionary infrared capabilities, will directly observe numerous young rogue planets and characterize their atmospheres in detail. Ground-based, extremely large telescopes, with primary mirrors 30 to 40 meters in diameter, will provide complementary observations with even higher resolution. Theoretical work on planet formation and ejection mechanisms will help interpret these observations, providing context for the population statistics of rogue planets. Improvements in our understanding of planetary interiors and cooling processes will refine age estimates and assessments of internal conditions, including the potential for subsurface oceans. Perhaps most excitingly, the combination of these advances might allow astronomers to identify rogue planets with characteristics suggesting habitability. While conclusively detecting life on such distant and dim objects remains beyond our current capabilities, identifying planets with the right mass, age, and hint of appropriate atmospheric composition to potentially harbor life would be a profound discovery. For now, the study of rogue planets remains in its infancy. The objects we have confirmed represent just a tiny fraction of the predicted population. Each detection method has provided a glimpse into a different segment of the rogue planet spectrum, like pieces of a puzzle that has only begun to be assembled. Yet even with our limited observations, it is clear that rogue planets are not rare anomalies, but common inhabitants of our galaxy. They drift through the vast spaces between stars, cold and dark, but not necessarily dead. To unlock their secrets, we must first find them. Rogues do not travel alone. They shape the galaxy as they roam. Beyond their significance as individual objects, rogue planets collectively influence and are influenced by the broader dynamics of our Milky Way galaxy. These wandering worlds, numbering potentially in the trillions, represent a significant component of the galactic mass, their gravitational effects subtly shaping the evolution of the galaxy over billions of years. To understand how rogue planets interact with the Milky Way, we must first consider the structure of our galaxy. The Milky Way is a barred spiral galaxy approximately 100,000 light-years in diameter, consisting of several distinct components. The central bulge, dense with stars, surrounds a supermassive black hole. Spiral arms, where most active star formation occurs, extend outward through the galactic disk. Beyond the visible disk lies the galactic halo, a roughly spherical region containing globular clusters, ancient stars, and vast amounts of dark matter. Rogue planets can be found throughout these regions, though in varying concentrations. Those ejected from stellar systems would initially share the distribution of stars, concentrated in the galactic disk and central bulge. Over time, gravitational interactions would scatter some into more inclined orbits, gradually populating the galactic halo. If some rogue planets form in isolation, their distribution might differ, potentially matching the distribution of molecular clouds where star formation occurs. Like stars, rogue planets orbit the galactic center, but their paths may be more varied and eccentric. A typical star in our galactic neighborhood completes one orbit of the Milky Way in about 250 million years, a period astronomers call a cosmic year. Rogue planets would have similar orbital periods, though with substantial variation depending on their distance from the galactic center and the eccentricity of their orbits. These orbits are not fixed, but evolve over time through interactions with other galactic components. Massive objects like giant molecular clouds can gravitationally perturb the paths of rogue planets, sending them on new trajectories. Spiral arms, with their increased density of stars and gas, can similarly alter rogue planet orbits as the planets pass through them. Over billions of years, these perturbations cause a process called phase mixing, where objects that initially shared similar orbits gradually disperse throughout the galaxy. This process would be particularly pronounced for rogue planets, as their relatively small masses make them more susceptible to gravitational perturbations than stars. While individual rogue planets have minimal gravitational effect on their surroundings, the collective gravitational influence of trillions of these objects could be substantial. If rogue planets indeed outnumber stars by orders of magnitude, their combined mass might account for a non-negligible fraction of the galactic visible matter. This collective mass would contribute to the overall gravitational field of the galaxy, influencing the orbits of stars and the rotation curve of the Milky Way. While dark matter remains the dominant component shaping galactic dynamics, accounting for about 85% of the matter in the universe, the contribution of rogue planets to the visible matter inventory could be significant enough to warrant consideration in detailed models of galactic evolution. One intriguing possibility is that rogue planets might account for some fraction of the galactic missing mass problem. Observations of the rotation of galaxies indicate that they contain more mass than can be accounted for by visible stars and gas. While most of this missing mass is attributed to dark matter, a population of rogue planets massive enough to influence galactic rotation, but too dim to have been detected, could contribute a small portion of this missing mass. Current estimates suggest that this contribution would be modest. Even if rogue planets outnumber stars by 100 to 1, their total mass would likely be less than the mass of the stars themselves, as most rogue planets would be smaller than the average star. Nevertheless, as we refine our census of the rogue planet population, their collective gravitational influence will need to be incorporated into increasingly precise models of galactic dynamics. Beyond their gravitational effects, rogue planets may play other roles in galactic evolution. As they travel through the interstellar medium, they sweep up gas and dust, potentially altering local density distributions. A massive gas giant rogue planet passing through a molecular cloud might create a wake in the gas, possibly triggering compression that could influence star formation processes. The passage of rogue planets through planetary systems represents another fascinating area of interaction. Given the vast number of both stars and rogue planets in the galaxy, such encounters must occur with some regularity over astronomical timescales. What happens when a rogue planet passes through a planetary system? The outcome depends on several factors, including the mass of the rogue planet, its velocity relative to the system, and how closely it approaches the star or its planets. In most cases, the encounter would be distant enough that its effects would be minimal, perhaps slightly perturbing the orbits of outer planets before the rogue continues on its way. In rarer cases of closer encounters, the gravitational effects could be more dramatic. A massive rogue planet passing near the outer reaches of a planetary system might capture or eject objects from the system's Oort cloud, the reservoir of comets that surrounds most stellar systems at distances of thousands to tens of thousands of astronomical units from their stars. Such perturbations could send comets plunging toward the inner system, potentially impacting planets and triggering extinction-level events similar to what may have ended the reign of dinosaurs on Earth. Alternatively, the rogue planet might capture comets or even small planets from the system, acquiring moons to accompany it on its solitary journey. In the most extreme and exceedingly rare scenario, a rogue planet might be captured by a stellar system, transitioning from a wanderer to a bound planet. This would require the rogue planet to lose energy during its passage through the system, perhaps through gravitational interactions with existing planets, or by passing through a dense circumstellar disk in a young system. Once captured, the rogue would become a new member of the planetary system, likely in a distant, highly eccentric orbit that would gradually circularize over millions of years through interactions with other system components. Conversely, close encounters between rogue planets and stellar systems can lead to the ejection of planets, creating new rogues. This process, occurring throughout the galaxy over billions of years, represents a kind of cosmic recycling. where planetary systems exchange mass with the wider galactic environment. Some of the rogue planets we might detect today could have once orbited stars now hundreds of light years away, while some planets currently orbiting nearby stars might once have been rogues. This exchange extends beyond whole planets to include smaller objects. Asteroids and comets ejected from planetary systems by interactions with massive planets or passing stars become interstellar objects, drifting between star systems. The recent discoveries of Oumuamua and Comet Borisov, the first confirmed interstellar visitors to our solar system, demonstrate that such objects exist and occasionally pass through our neighborhood. Rogue planets likely play a role in the transport of these smaller objects through the galaxy. A passing rogue might capture an asteroid or comet from one system and, eons later, lose it to another system, facilitating a kind of material exchange across vast distances. This process could have implications for the spread of organic compounds, or even simple life forms across the galaxy, a concept known as panspermia. The extreme timescales involved in these galactic processes can be difficult to grasp. Stars orbit the Milky Way so slowly that our Sun has completed only about 20 orbits since its formation 4.6 billion years ago. Over such vast periods, rare events become inevitable. The Sun has likely had close encounters with other stars multiple times in its history, and encounters with rogue planets, while less well studied, may have been even more common given their potentially greater numbers. The galactic context of rogue planets also includes the broader picture of galaxy formation and evolution. As galaxies interact and sometimes merge, enormous gravitational disturbances ripple through their structures. These interactions can eject not just planets, but entire stars from galaxies. The intergalactic space between the Milky Way and neighboring galaxies likely contains stars and rogue planets torn from their home galaxies by these violent processes. Some of the most extreme examples would be rogue planets ejected at velocities sufficient to escape the gravitational pull of the Milky Way entirely. These hypervelocity planets would be launched on trajectories taking them into intergalactic space, where they might wander for billions or even trillions of years, far from any star, the ultimate cosmic nomads. The mechanisms capable of accelerating planets to such extreme velocities include close encounters with binary star systems, where complex three-body interactions can result in one object being flung away at high speed, or interactions with a supermassive black hole at the galactic center, which can accelerate objects through a gravitational slingshot effect. While most rogue planets would travel at velocities similar to those of nearby stars, roughly 220 kilometers per second relative to the galactic center, these hypervelocity planets might reach speeds of over 1,000 kilometers per second. At such velocities, they could cross the entire diameter of the Milky Way in less than 100 million years and escape into intergalactic space in similar timeframes. The concept of rogue planets wandering through intergalactic voids, where the density of matter is 1,000,000 times lower than within galaxies, stretches our imagination to its limits. In such environments, these planets might travel for distances equivalent to dozens or hundreds of galaxy diameters before encountering another significant mass. The darkness and isolation would be absolute, broken only by the faint light of distant galaxies. Yet even in these extreme environments, the internal dynamics of the planets themselves would continue. Geological processes would gradually slow, but not cease entirely. Internal radioactive decay would continue to generate heat, and if subsurface oceans existed, they might remain liquid for extraordinary periods, insulated by thick ice crusts from the near absolute zero temperatures of intergalactic space. Returning to our own galaxy, the population of rogue planets is not static, but constantly evolving. New rogues are created through planetary ejection processes, while existing rogues can be captured by stellar systems. Some may collide with stars or other massive objects, though such events would be exceedingly rare given the vast emptiness of space. Others might be consumed when passing too close to the supermassive black hole at the galactic center. The age distribution of rogue planets likely spans the entire history of the galaxy. Some of the oldest may have been ejected from the first generation of planetary systems that formed around the earliest stars, more than 12 billion years ago. These ancient rogues would have witnessed much of the evolution of the Milky Way, their trajectories shaped by the changing gravitational landscape as the galaxy matured. In contrast, some of the youngest rogue planets may have been ejected from newly formed planetary systems within the last few million years, infants in cosmic terms. These young rogues would still be warm from their formation, potentially detectable by their infrared emission, and would not yet have traveled far from their birth systems. The diversity of the rogue planet population, in terms of age, mass, composition, and orbital characteristics, reflects the diversity of the planetary systems from which they originated and the varied processes that led to their ejection. This diversity represents a kind of living fossil record of planetary system evolution throughout the history of our galaxy. As our observational capabilities advance, we may begin to map the distribution of rogue planets in our galactic neighborhood, revealing patterns that provide insights into their origins and the dynamic processes that shape their journeys. The Nancy Grace Roman Space Telescope, with its unprecedented microlensing survey capabilities, could detect thousands of rogue planets and begin to establish their statistical properties as a population. In the more distant future, advanced gravitational wave observatories might detect the subtle ripples in spacetime caused by massive rogue planets accelerated to high velocities by close encounters with compact objects like neutron stars or black holes. These detections could provide a new window into the most dramatic events in the lives of these wandering worlds. The study of rogue planets in their galactic context connects the intimate details of planetary system formation and evolution with the grand scales of galactic dynamics. These wandering worlds serve as messengers, carrying information about their birth systems and the environments they have traversed on their long journeys. In their collective motions and characteristics, they encode a history of our galaxy that complements the stories told by stars and other galactic components. Rogues do not travel alone. They form a vast, dispersed community of worlds adrift in the cosmic ocean, influencing and being influenced by the dynamic processes that shape our galaxy. In their lonely journeys between the stars, they connect the familiar realm of planetary systems with the grander scales of galactic evolution. The unknown often sparks the imagination and guides discovery. Long before astronomers confirmed the existence of rogue planets, writers, filmmakers, and artists had envisioned worlds drifting alone through the cosmic void. These creative explorations have both reflected and shaped our understanding of rogue planets, demonstrating the powerful interplay between scientific discovery and artistic imagination. Science fiction, in particular, has embraced the concept of planets without stars, using these lonely worlds as settings for stories that explore themes of isolation, survival, and the resilience of life in extreme environments. These fictional portrayals have evolved alongside our scientific understanding, sometimes anticipating discoveries that would later be confirmed by astronomers. One of the earliest and most influential depictions of a rogue planet appears in the 1936 story by British writer Olaf Stapledon, titled Star Maker. In this visionary work, Stapledon describes a planet he calls the Wanderer, ejected from its original star system and drifting through interstellar space. Despite the freezing conditions on its surface, life persists in the planet's deep oceans, warmed by internal heat. This remarkably prescient description aligns with current scientific thinking about potential habitats for life on rogue planets, written decades before the first exoplanets were discovered. The concept gained further prominence in science fiction during the mid-20th century, particularly in the works of authors like Isaac Asimov and Arthur C. Clarke. In Asimov's 1956 novel The Naked Sun, he mentions worlds between the stars, speculating that they might be numerous but difficult to detect due to their darkness. Clarke, in his 1953 story The Parasite, imagines a rogue planet passing through our solar system, bringing with it alien life forms that threaten humanity. As scientific understanding of planetary formation advanced in the latter part of the 20th century, the concept of ejected planets gained credibility in astronomical circles. This scientific evolution was reflected in increasingly sophisticated fictional treatments of rogue planets. Authors began to explore not just the physical characteristics of these worlds, but their potential as habitats and their significance in the broader cosmological context. Powell Anderson's 1970 novel Tau Zero features a rogue planet called Kamiroy that maintains a habitable temperature through artificial means after being ejected from its star system. This introduces a theme that would become common in later science fiction, the technological adaptation that might allow intelligent life to survive on a wandering world. Film and television have also embraced rogue planets as dramatic settings. Perhaps the most famous example comes from the Doctor Who series, which introduced the planet Mondas, Earth's twin, that drifted away from the solar system eons ago. The harsh conditions of this wandering world forced its inhabitants, the Cybermen, to replace their organic body parts with mechanical components to survive, transforming them into the cyborg antagonists that would become iconic villains in the series. The 1997 film Alien Resurrection, directed by Jean-Pierre Jeunet, features a brief but memorable depiction of a frozen rogue planet. The ship's computer identifies it as an icebound world, alone in space, that will serve as the setting for the film's climactic confrontation. Though scientifically questionable in some aspects, the visual portrayal of a planet in complete darkness, covered in ice under an eternally black sky, effectively conveys the alien nature of such environments. More recent science fiction has continued to develop the concept in increasingly nuanced ways. Liu Cixin's epic trilogy Remembrance of Earth's Past, which begins with the novel The Three-Body Problem, features a civilization on a planet in a triple star system who must cope with unpredictable environmental conditions. Though not technically a rogue planet, the world's chaotic climate, due to its complex orbit, presents challenges that resonate with themes associated with planets in extreme environments. Cixin Liu later explored the concept of rogue planets more directly in short stories like The Wandering Earth, adapted into a blockbuster Chinese film in 2019. In this story, humanity transforms Earth itself into a kind of artificial rogue planet, equipping it with enormous engines to escape the solar system when the sun begins to expand. This imaginative scenario inverts the typical narrative, presenting the rogue state as a solution rather than a problem, a means of survival rather than a threat. The 2008 film Pandorum uses a generation ship headed for a rogue planet called Tanis as its premise. This habitable world without a sun is presented as humanity's last hope after Earth becomes overpopulated. The film draws on scientific concepts like geothermal heating to explain how such a planet could support life, though it takes considerable liberties with the science. In the realm of video games, the Mass Effect series features a rogue planet called Mnemosyne, described as a gas giant ejected from its star system. The game portrays it as extremely cold on the surface, but somehow maintaining enough internal heat to support a research station. While not scientifically rigorous, such depictions help popularize the concept of worlds that exist beyond the warming light of stars. The independence from a parent star makes rogue planets particularly useful narrative devices for science fiction. Without the constraints of orbital mechanics or the habitable zone concept, authors can more freely explore unusual environmental conditions and their effects on potential inhabitants. The inherent isolation of these worlds also creates natural settings for stories about self-contained civilizations, developing in complete separation from other intelligent life. Science fiction has also explored more speculative aspects of rogue planets that extend beyond current scientific understanding. Some stories suggest that advanced civilizations might deliberately engineer rogue planets as arks or as hidden refugees from cosmic threats. Others propose that naturally occurring rogue planets might serve as interstellar transportation for intelligent species, carrying them across the vast gulfs between stars over millions of years. The 1999 novel Manifold Space by Stephen Baxter features a rogue planet called Cruthen that contains an enormous machine built by an ancient alien civilization. The machine preserves life through the cold, dark journey between stars. This concept of engineered worlds drifting through space appears in numerous other works and reflects the human tendency to imagine how technology might overcome even the most extreme environmental challenges. Beyond direct portrayals of rogue planets, the concept has influenced broader science fiction themes related to interstellar travel and colonization. Generation ships, spacecraft designed to support multiple generations of travelers on journeys lasting centuries or millennia, share conceptual similarities with rogue planets. Both represent self-contained biospheres traveling through the void of space, independent of external energy sources like stars. In Greg Egan's 2000 nautical novel Diaspora, advanced civilizations create artificial habitats called polises that exist as virtual environments supported by massive computational infrastructure. Some of these polises are housed in planet-sized objects deliberately sent wandering through interstellar space as a way to survive cosmic catastrophes. This represents perhaps the ultimate extension of the rogue planet concept, reimagined not as a natural phenomenon, but as the deliberate creation of intelligence. This science-fictional exploration of rogue planets has contributed to public understanding and scientific interest in these objects. Many astronomers and planetary scientists cite science fiction as an early influence that drew them to their fields of study. The vivid portrayals of unusual worlds in literature and film help make abstract astronomical concepts more concrete and engaging for both scientists and the general public. The relationship between science fiction and astronomy has always been reciprocal. Scientific discoveries inspire fictional explorations, which in turn stimulate interest in further research. In the case of rogue planets, fiction anticipated science in many ways, imagining wandering worlds long before their existence was confirmed. Now that we know such planets are real, fiction continues to explore their implications, sometimes suggesting research directions that scientists might not otherwise have considered. For instance, the fictional portrayal of subsurface oceans on rogue planets, kept liquid by internal heat, preceded serious scientific consideration of such possibilities. Now, the search for evidence of subsurface water on rogue planets represents an active area of astronomical research with implications for the potential habitability of these worlds. The cultural impact of rogue planets extends beyond conventional science fiction into other creative domains. Artists have found inspiration in the concept of worlds adrift in darkness, creating paintings, digital art, and music that attempt to capture the haunting beauty and isolation of planets without suns. These artistic interpretations help us emotionally connect with astronomical phenomena that exist far beyond our direct experience. Composers have created musical pieces that attempt to evoke the cold, lonely journeys of rogue planets. Visual artists have imagined landscapes under skies without a sun, where the only illumination comes from distant stars or the faint glow of geological features. Poets have used rogue planets as metaphors for human experiences of isolation, resilience, and the search for meaning in a vast, seemingly indifferent universe. In the realm of speculative science communication, rogue planets have become popular subjects for illustrated books, documentary films, and digital planetarium shows. These works strive for scientific accuracy while engaging the public imagination, often drawing on the same evocative imagery that makes rogue planets compelling in fiction. The discovery of actual rogue planets has only enhanced their cultural significance. When astronomers announced the identification of CFBD SIR 2149-0403 in 2012, media coverage frequently referenced science fiction, drawing parallels between the real object and its fictional predecessors. Similar connections were made with the discovery of PSOJ 318.5-22 in 2013, highlighting how fiction and science inform each other in the public consciousness. This interplay between imagination and discovery reflects a broader pattern in the history of science. Many scientific advances began as speculative ideas, considered implausible or even impossible until evidence gradually accumulated in their favor. The concept of continental drift, now accepted as plate tectonics, faced skepticism for decades before becoming scientific orthodoxy. Similarly, the idea of planets orbiting other stars remained in the realm of fiction until the first confirmed exoplanet discovery in 1995. Rogue planets represent a particularly compelling example of this pattern. The idea of planets existing independently of stars seemed counterintuitive in an era when planets were defined by their relationship to stars. Yet, imaginative exploration of the concept preceded and perhaps facilitated its scientific acceptance. By envisioning how such worlds might exist, fiction created conceptual space for scientists to consider and eventually confirm their reality. As our understanding of rogue planets continues to evolve, fiction will likely adapt and incorporate new scientific insights. Future stories may explore aspects of these worlds that we can barely imagine today, just as current fiction builds on discoveries that would have astounded earlier generations of writers and scientists. The fascination with rogue planets in both scientific and cultural contexts speaks to something fundamental in human nature. We are drawn to the mysterious, the extreme, the boundary cases that challenge our assumptions. Planets without stars represent such boundaries, forcing us to reconsider what we mean by a planet and where habitable environments might exist. In their solitary journeys through the cosmic void, rogue planets embody both the harshness and the wonder of the universe. They remind us that the cosmos operates on scales of time, distance, and possibility far beyond our everyday experience. Fiction helps us bridge that gap, translating astronomical concepts into human terms and connecting abstract knowledge with emotional understanding. The unknown often sparks the imagination, and the imagination guides discovery. In this reciprocal relationship between science and fiction, between observation and speculation, we find one of the most productive dynamics in human intellectual history. Rogue planets, once purely imaginary and now confirmed as real, exemplify this dynamic, showing how the boundary between the known and the unknown continues to shift as we explore the universe around us. Each rogue planet is a mystery waiting to be understood. As we look to the future of astronomy and planetary science, these wandering worlds promise to play an increasingly important role in our understanding of the cosmos. Advances in observational technology, theoretical modeling, and perhaps even direct exploration will gradually unveil the secrets of rogue planets and their significance for fundamental questions about planetary formation, galactic evolution, and the potential for life beyond Earth. The next decade will bring revolutionary new capabilities for detecting and studying rogue planets. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct the most comprehensive microlensing survey ever attempted. With its wide field of view and exceptional sensitivity, the Roman telescope is expected to detect thousands of rogue planets, ranging from gas giants down to objects the size of Mars or smaller. This unprecedented census will reveal the true abundance and mass distribution of rogue planets, allowing astronomers to determine whether they truly outnumber stars, as some models predict. By analyzing the statistics of these detections, scientists will gain insights into the mechanisms that create rogue planets and their role in planetary system evolution. Complementing the Roman telescope's microlensing survey, the James Webb Space Telescope will provide detailed characterization of directly detected rogue planets. With its unparalleled infrared sensitivity, Webb can observe the faint thermal emission from young, massive rogue planets and analyze their atmospheric composition through spectroscopy. These observations will help determine whether rogue planets form primarily through ejection from planetary systems or through direct collapse in isolation. Ground-based observatories will also contribute significantly to rogue planet studies. The new generation of extremely large telescopes, including the 30-meter telescope, the Giant Magellan Telescope, and the European Extremely Large Telescope, will provide unprecedented resolution for direct imaging of nearby rogue planets. When combined with advanced adaptive optic systems that correct for the blurring effects of Earth's atmosphere, these telescopes will be able to detect fainter and smaller rogue planets than ever before. Advances in radio astronomy, particularly with facilities like the Square Kilometre Array, may enable the detection of magnetic fields around massive rogue planets. Such detections would provide crucial information about the internal structure of these objects, including whether they maintain partially molten cores that could support subsurface oceans potentially habitable for some form of life. Beyond improvements in observational capability, advances in theoretical modeling and computational techniques will enhance our understanding of rogue planets. More sophisticated simulations of planetary system formation and evolution will clarify the mechanisms and frequency of planetary ejections. These models will incorporate increasingly realistic physics, including the effects of gas dynamics, radiation, and magnetism on the chaotic early evolution of planetary systems. Similarly, improved models of planetary interiors will provide more accurate predictions of how rogue planets cool over time and whether they can maintain internal heat sources sufficient to support liquid water beneath their frozen surfaces. These models will build on data from missions to the outer solar system, where objects like Europa and Enceladus offer nearby analogues for the potential subsurface environments of rogue planets. One of the most exciting prospects for future rogue planet research involves the potential detection of biosignatures, chemical evidence for life. While direct detection of life on rogue planets remains beyond our current capabilities, the next generation of telescopes might detect atmospheric components that suggest biological activity, particularly for rogue planets that retain substantial atmospheres. For instance, certain combinations of gases that would normally react with each other, like oxygen and methane, can persist together only if continuously replenished, possibly by biological processes. If such combinations were detected in the tenuous atmosphere of a rogue planet, it would be a tantalizing, though not conclusive, hint of biological activity. More likely, we might detect evidence of subsurface oceans through plumes of water vapor escaping through cracks in an icy surface, similar to the plumes observed on Saturn's moon Enceladus. The composition of these plumes could provide insights into the chemical environment of the subsurface ocean and its potential to support life. The scientific significance of rogue planets extends far beyond the objects themselves. As laboratories for extreme planetary environments, they help us understand the resilience of planetary systems and potentially of life itself. They challenge our planet classification schemes and force us to consider worlds beyond the traditional definition of planets as bodies orbiting stars. Rogue planets also provide unique opportunities to study planetary interiors and evolution without the complicating factor of stellar irradiation. A planet drifting alone through space, heated only by its internal processes, offers a cleaner system for testing models of planetary cooling and geological activity than planets subject to the constant energy input of a nearby star. The survival mechanisms of any hypothetical life on rogue planets would necessarily differ from those that evolved on Earth, providing insights into the adaptability and diversity of life under extreme conditions. While we have no evidence that life exists on any rogue planet, the theoretical possibility expands our conception of habitable environments and informs the search for life elsewhere in the universe. From a technological perspective, future investigation of rogue planets might eventually include direct exploration. While interstellar travel remains far beyond our current capabilities, rogue planets passing relatively close to our solar system could become targets for advanced propulsion systems now in the early stages of development. Concepts like solar sails accelerated by powerful lasers or fusion propulsion might someday achieve the velocities necessary to reach nearby rogue planets within a human lifetime. Such missions would likely begin with flybys, capturing detailed observations as spacecraft speed past these dark worlds. Later, more ambitious missions might include orbiters or even landers designed to directly sample the surface or penetrate the ice to study any subsurface oceans. These missions, while speculative and certainly decades away, represent the logical extension of our robotic exploration of the solar system. Just as spacecraft like Voyager, Cassini, and New Horizons have revolutionized our understanding of the outer planets and their moons, future missions to nearby rogue planets would transform our knowledge of these wandering worlds. In the nearer term, we might detect rogue planets passing through our own outer solar system. While no such objects have yet been confirmed, statistical models suggest that rogue planets occasionally pass within a few hundred astronomical units of the Sun. The upcoming Legacy Survey of Space and Time with the Vera C. Rubin Observatory will scan the entire visible sky every few nights, potentially catching the reflected sunlight from large rogue planets passing through our cosmic neighborhood. Such a nearby rogue planet would present an unprecedented opportunity for detailed study. Even with existing telescope technology, astronomers could determine its composition, search for atmospheric signatures, and measure its magnetic field if present. This would provide ground truth for models of rogue planet characteristics that could then be applied to more distant objects. Beyond the scientific implications, rogue planets challenge us philosophically. They embody cosmic isolation, worlds truly alone in the void, separated from the warming light and stabilizing influence of stars. Yet they also represent resilience, the potential for planets and perhaps even life to persist in the most extreme environments. The existence of rogue planets reminds us that our solar system, with its relatively orderly arrangement of planets in nearly circular orbits, may not be the norm. The processes that form planetary systems are messy and chaotic, with many worlds formed only to be ejected into solitary journeys through interstellar space. This perspective humbles us, suggesting that our comfortable position around a stable star may be more fortunate than we once assumed. At the same time, rogue planets expand our conception of where life might exist in the universe. If even a small fraction of these wandering worlds maintain conditions suitable for some form of life, the total habitable real estate in the galaxy could be far greater than just the planets orbiting in the habitable zones of stars. This realization dramatically increases the potential environments where we might someday find evidence of life beyond Earth. The study of rogue planets connects to broader questions in astronomy and planetary science. How do planetary systems typically evolve? How stable are planetary orbits over billions of years? How resilient is life in the face of extreme environmental changes? By studying these cosmic wanderers, we gain insights into these fundamental questions that impact our understanding of our own planet and its future. As we develop more powerful tools for detecting and studying rogue planets, we can expect a cascade of discoveries that will refine and potentially transform our understanding of these objects. The current sample of confirmed rogue planets remains small, limiting our ability to draw firm conclusions about their typical characteristics or formation pathways. But with thousands of new detections anticipated in the coming decades, patterns will emerge that illuminate the histories and properties of these wandering worlds. One intriguing possibility is that rogue planets might serve as stepping stones for interstellar exploration. If they are as numerous as current estimates suggest, the average distance between rogue planets would be much smaller than the distance between stars. Future interstellar missions might use rogue planets as waypoints, taking advantage of their gravity for course adjustments or as sources of raw materials for refueling and repairs. Even more speculatively, if some rogue planets maintain conditions suitable for life, they could potentially serve as oases in the interstellar desert, natural habitats that could support human outposts on the long journey between stars. While such scenarios remain firmly in the realm of far future speculation, they illustrate how the discovery of rogue planets has expanded our conception of the possibilities for humanity's long-term future among the stars. From a more immediate and practical perspective, the study of rogue planets forces us to reconsider our definitions and categories in planetary science. The traditional definition of a planet as a body that orbits a star no longer encompasses the full diversity of planetary objects we now know exist. Some astronomers have proposed new classification schemes that account for free-floating planets, acknowledging that a planet's relationship to a star may be temporary rather than defining. This rethinking extends to our conception of habitability. The habitable zone concept, which defines the region around a star where liquid water could exist on a planet's surface, has been central to our search for potentially life-supporting worlds. Rogue planets challenge this star-centered view of habitability, suggesting that internal heat sources might create habitable niches independent of stellar warming. As we expand our census of rogue planets and develop more sophisticated models of their interiors and evolution, we may identify specific categories that are most promising for habitability. Super-Earth-sized rogue planets with thick hydrogen atmospheres might retain enough heat to maintain liquid water oceans for billions of years. Gas giants with large moons might experience enough tidal heating to create habitable environments on their satellites, even in the absence of a star. The implications extend to astrobiology and the search for life beyond Earth. If habitable environments can exist on rogue planets, the total habitable volume in the galaxy increases dramatically. Moreover, life on rogue planets would be isolated from many of the hazards that threaten starbound worlds, such as stellar flares, intense radiation, and eventually, the death of the parent star. In the very long term, as stars gradually exhaust their nuclear fuel over trillions of years, rogue planets might become the last refugees for life in an aging universe. This cosmic longevity gives rogue planets a significance beyond their current properties. While stars have finite lifespans, ranging from millions to trillions of years depending on their mass, rogue planets could persist almost indefinitely. Their internal heat would gradually diminish, but on timescales of tens of billions of years or longer. In the far future of the universe, when star formation has ceased and existing stars have burned out, rogue planets might be among the few remaining havens for complexity and potentially for life. The possibility that rogue planets might harbor life also raises questions about how such life would perceive the universe. Evolution on Earth has been shaped by the day-night cycle, by seasonal changes, and by the visibility of stars, planets, and other celestial objects. Life on a rogue planet would experience none of these. Without visible stars, would such life develop astronomy? Without cycles driven by a parent star, how would it measure time? These questions invite us to consider how fundamentally different cognition and culture might be if evolved in isolation from the broader cosmic environment that has influenced life on Earth. While such speculations may seem distant from the immediate concerns of rogue planet research, they illustrate the profound implications of these discoveries. By expanding our understanding of where planets can exist and how they can evolve, rogue planets enrich our conception of the universe and our place within it. They remind us that the cosmos is more diverse, more dynamic, and potentially more hospitable to life than we once imagined. As our observational capabilities and theoretical models advance, we can expect rogue planets to move from the periphery of planetary science to a central position. Their abundance, diversity, and unique characteristics make them essential objects of study for understanding the full spectrum of planetary environments. Each discovery brings new insights and raises new questions, driving the continued evolution of our understanding. The journey of exploration has only just begun. With each new detection, each refinement of our models, each advance in our observational capabilities, we draw closer to understanding these enigmatic wanderers. In their cold, dark solitude, rogue planets carry secrets of planetary formation, of cosmic evolution, and perhaps even of life's potential beyond the nurturing light of stars. Each rogue planet is indeed a mystery waiting to be understood, a testament to the wondrous complexity and diversity of our universe. Adrift in the cosmic sea, rogue planets hold their secrets close. They remind us that the universe is vast, mysterious, and full of wonders still waiting to be found. As our journey of discovery comes to a close, we reflect on these solitary travelers and their significance in the grand tapestry of the cosmos. The darkness surrounding rogue planets is not emptiness but possibility. In the absence of a star's overwhelming light, subtle phenomena emerge that might otherwise be obscured. the faint auroras generated as these worlds pass through the interstellar medium, the slow geological processes driven by internal heat rather than external warming, the potential hidden oceans where life might find unexpected footholds in the cosmic wilderness. These wandering worlds challenge our perception of what a planet can be. No longer confined to orderly orbits around nurturing stars, planets can exist as independent entities, traveling the vast gulfs between stellar systems. Their journeys may span billions of years and thousands of light years, witnesses to the slow evolution of galactic structures that stars themselves might not survive to see. For all their alien nature, rogue planets connect to our own world in surprising ways. The same processes that created these cosmic nomads shaped our solar system. Gravitational interactions between young planets likely ejected some worlds from our system while rearranging others into the configuration we know today. Our comfortable home around a stable star exists in part because other worlds were cast into the darkness. Moreover, the possibility that life might exist in the subsurface oceans of some rogue planets expands our conception of habitability beyond the traditional notion of a habitable zone around a star. Life, with its remarkable adaptability, might flourish in environments we once considered too extreme for biological processes. This realization multiplies many-fold the potential abodes for life in our galaxy and beyond. Consider for a moment the perspective from the surface of a rogue planet. Standing on a world without a sun, you would see no daybreak, no sunset, no cycles of light and dark to mark the passage of time. The sky would remain eternally black, sprinkled with the unchanging points of distant stars and galaxies. Without the blinding glare of a nearby star, the full majesty of the cosmic panorama would be visible at all times, a celestial display unmatched by the night sky of any planet bound to a star. The cold would be profound, the surface likely frozen to temperatures approaching absolute zero. Any atmosphere would have long since condensed onto the surface as exotic ices. Yet beneath that frozen shell, warmed by the planet's internal heat, oceans might swirl in perpetual darkness, their currents driven by the subtle interplay of thermal gradients and the rotation of the planet itself. In such an ocean, life might develop unlike anything we know on Earth. Without photosynthesis, organisms would rely on chemosynthesis, extracting energy from chemical reactions rather than sunlight. Their senses would be adapted to perpetual darkness, perhaps developing forms of bioelectrical communication or extraordinary sensitivity to vibration and chemical gradients. The evolution of such life, isolated from the wider galaxy by kilometers of ice, might proceed for billions of years undisturbed by cosmic catastrophes that periodically reset evolution on starbound worlds. Shielded from stellar flares, asteroid impacts, and eventually the death of parent stars, life on rogue planets might achieve forms of complexity and adaptation we can scarcely imagine. These possibilities represent the frontier of our scientific understanding, where observation meets speculation in the quest to comprehend the full diversity of planetary environments and the potential for life beyond Earth. The confirmation that rogue planets exist in large numbers has already expanded our cosmic horizons. Future discoveries will surely reveal even more wonders as we develop the tools to study these elusive objects in greater detail. The rogue planets drifting through our galaxy embody both solitude and connection. They are isolated from the warming light of stars, yet bound to the galaxy by gravity, their paths shaped by encounters with other objects in an endless cosmic dance. They remind us that even in apparent isolation, nothing in the universe exists truly alone. Perhaps most profoundly, rogue planets challenge us to reconsider our place in the cosmos. Our sun, while essential for life as we know it, is just one star among hundreds of billions in our galaxy. The planets of our solar system, while familiar and well studied, represent just a tiny fraction of the planetary population. The conditions that we consider normal, a planet warmed by a stable star, may be the exception rather than the rule in a universe where rogue planets potentially outnumber those bound to stars. This perspective does not diminish our home, but enriches our understanding of it. Earth exists within a broader context of planetary environments ranging from the hellish heat of worlds like Venus to the frigid darkness of rogue planets adrift between the stars. By studying this full spectrum of possibilities, we gain deeper insights into the processes that shaped our own world and the conditions that allowed life to flourish here. As we gaze up at the night sky, we now know that between the points of light we see as stars, dark worlds wander unseen. They carry their secrets through the void, preserving conditions from the early days of our galaxy, harboring potential environments for life unlike any we have yet discovered, and challenging our assumptions about what constitutes a planet. The exploration of rogue planets has only begun. With each new detection, each advancement in observational capability, each refinement of our theoretical models, we draw closer to understanding these enigmatic wanderers. Their stories, once they are fully told, will enrich our conception of the universe and our place within it. Adrift in the cosmic sea, rogue planets journey on, silent witnesses to the grandeur and diversity of our universe. They remind us that even in the coldest darkness, complexity and perhaps even life might flourish. They embody the profound truth that the cosmos contains far more wonders than we have yet imagined, waiting to be discovered by those curious enough to look beyond the light into the darkness between the stars.